Hello everyone, welcome to the lecture 2 for this series of lectures where I am talking about the deformation theory of instantons on nearly G2 manifolds. I am Ragini and this is lecture 2 as I already mentioned. So in lecture 1 we covered the introduction to G2 structures and I described two equivalent ways how you can define a G2 structure on a 7-dimensional manifold, and today we'll be focusing on the gauge theory on G2 manifolds. So basically I will define how we can define an instanton, a G2 instanton on a manifold with a G2 structure, and we'll also talk about the infinitesimal deformations of a G2 instanton on a nearly G2 manifold. So this is done in lecture 1 and this we'll cover today basically in this lecture, and then the last part, the deformations, will be covered, the canonical connection will be covered in lecture 3. So let's begin. And so since we are talking about gauge theory, obviously we'll have to talk about bundles over our manifold M. So I'll denote by this P by a principal G bundle where G is a Lie group, and then a connection I'll denote by this capital A, a connection one form on P or just a connection on P, and the curvature associated to the connection A will be denoted by Fa. So this is the setup. I have this bundle P over just to remind you, M phi. So I'll denote a manifold with G2 structure by phi and eta. So here this phi is the non-degenerate 3 form and eta is the unit real spinor. So we saw in lecture 1 that you can define the G2. So this notation is a bit repetitive because you can get phi from eta and eta from phi, but I'm just writing it just so to keep the notation clear. So this phi and eta both defines the same G2 structure on a 7-dimensional manifold M, and we say that the connection A is a G2 instanton on this manifold with this G2 structure if the curvature is in the omega 214 part. So if you remember from lecture 1, we discussed that how whenever I have a manifold with a G2 structure, there's an action of the Lie group G2 which breaks the space of two forms in two irreducible components, omega 27 and omega 214. Here this omega 214 was isomorphic to the adjoint representation G2 of the Lie algebra, and we say that, and then for the curvature we will say that that the connection A is a G2 instanton if the two form part of the curvature Fa is in omega 214, and this is sort of the definition that is equivalent to many things, and one of the things is that that means that it is in the plus eigenvalue of this Fa wedge phi, and then the second equivalent equation is that Fa wedge psi equals to 0, and the third equivalent definition is that Fa dot eta equals to 0. So this definition actually we can see right away by just using the fact that Fa is in the Lie algebra of G2 in some sense, because eta, as we know is the G2 structure, is preserved by the action of the Lie group zeta, and this is sort of the action of the Lie algebra of G2 on this eta, and thus since it's like the infinitesimal action and eta is preserved by the Lie group G2, it will be annihilated by the Lie algebra of the Lie group G2, and that's why we get that Fa dot eta has to be 0. So these are some equivalent definitions of a G2 instanton. One more thing here is that this definition has nothing to do with the type of G2 structure. So this definition is true for any G2 structure. What happens is when we have a specific type of torsion, the properties of G2 instantons might differ, but the definition remains the same. So one thing, once we have an instanton, it's a natural question to ask whether it's Yang-Mills, and that just means that whether dA star Fa is 0, and so we will see that if we take dA star of Fa, then that is just given by star dA star Fa, and from this second equation we have that this is just star dA Fa wedge phi. You can now break the dA, just split the dA within the wedge, and what we get is that is this, and here the first term vanishes by the G2 Bianchi identity, just the Bianchi identity, and then we are left with a star of Fa wedge d phi. So dA star Fa is just a star of Fa wedge d phi, and now from this equation it's very easy to see that if d phi is 0, then our instanton is Yang-Mills, but other than that, for nearly G2, for nearly G2, just to recall you, we take d phi equals to 4 psi, and so again A would be Yang-Mills, because for nearly G2 we will get Fa wedge psi, and Fa wedge psi is also 0 since Fa is in omega 214. So a G2 instanton is Yang-Mills for closed G2 structures and nearly G2. So, and of course torsion free is included in the closed G2 structure case, so it is Yang-Mills for torsion free, and it's also Yang-Mills for nearly G2, and this is one of the reasons why it is useful to study instantons on nearly G2 manifolds. So, but there is a difference between nearly G2 manifolds and torsion free with respect to the G2 instantons. So for both of them, the G2 instanton is Yang-Mills, but for torsion free G2 structures, they are not just Yang-Mills, they are not just the critical points of the Yang-Mills energy functional, but they are also the absolute minimizers of the Yang-Mills energy functional, which is not true for the nearly G2 case. So for the torsion free, they are also stable critical points, but for the nearly G2, they are not the minimizers, they are not the absolute minimizers of the Yang-Mills energy functional. In fact, there was a counter example which was given by Gonzalo and Given in their paper Gauge theory on Euler-Wollasky spaces, where they explicitly describe a family of instantons, a family of connections, and then they show that the Yang-Mills energy is minimized using some other connection which is not a G2 instanton. So this is a major difference between G2 properties of G2 instantons on torsion free and on nearly G2. So nevertheless, G2 instantons on nearly G2 manifolds are still worth studying, and in today's topic and in today's lecture, we'll focus on studying the deformation theory of these instantons. So from now on, I will always fix m phi eta to be a nearly G2 manifolds, and on this manifold we'll describe this family of connections nabla T with totally skew symmetric torsion. What does totally skew symmetric torsion means is that the torsion is defined by a 3 form, or it's basically it's a 3 form, so it's a totally skew symmetric torsion. This family of totally skew symmetric connections is very much studied in detail by Ilkay Agricola and Thomas Friedrich in many papers, and the family is just given simply by this. So here this nabla T is a connection on the spinor bundle, and this nabla G is the lift of the Levi-Civita connection on the spinor bundle, and phi is just the 3 form phi, which we already know. So this describes, and here the torsion is isomorphic to T over 3 phi, which is, as you can see, is a 3 form. That's why it's totally skew symmetric torsion. And in this family, if we fix T equals to -1, then we can see that nabla -1 is 0. And so basically nabla -1 eta is 0, so the killing spinor eta is parallel with respect to the connection nabla -1, and that means that the holonomy of this connection nabla -1 is inside the Lie group G2. So if you remember from lecture 1, the holonomy of nabla 0, which is just the Levi-Civita connection, so if T is 0, we just get the Levi-Civita connection, it's inside S07 and not inside G2. This was the difference between nearly G2 and torsion free G2. Not only this, one can also show that this connection nabla -1 is actually a G2 instanton. So we readily have an example of a G2 instanton on a nearly G2 manifold. So for torsion free, the Levi-Civita connection is also a G2 instanton. But in the nearly G2 case, Levi-Civita connection is not a G2 instanton, but this nabla minus 1 is a G2 instanton. So in some sense, this nabla minus 1, or the, as we will now call it, the canonical connection, is an analog of the Levi-Civita connection on the nearly G2 manifold. And it was and it's usually known characteristic connection or canonical connection depending on the author. But whenever one says about the canonical connection or the characteristic connection on the nearly G2 manifold, this is what it is meant, and you can just think of it as an analog of the Levi-Civita connection on the nearly G2 manifold. And it was proved by Richard Clayton and Andrew Swan that there is a unique totally skew symmetric holonomy G2 connection on nearly G2 manifolds, and this is this connection. And the same thing is also true for nearly Kähler 6 manifolds. There also you can get a canonical connection, which is a G2 instanton, and it's also the unique totally skew symmetric torsion holonomy G2 connection on the nearly Kähler 6 manifold. So this is a good thing, because now we have an example of G2 instanton, which is just which we can then use to study the deformation space of this G2 instanton, and that is what we will do in lecture 3. We will try to describe the deformation space of this connection on homogeneous nearly G2 manifolds. So that is just a insight to what we are going to do in future lectures. So we have this family of connections, and this is a family of connections in a Spinor bundle. So we can define an associated Dirac operator. So this SM, that is just the Spinor bundle. Add P is the joint bundle related to the principal G bundle P over our manifold M, and on this we have this associated Dirac operator. So just to recall, the Dirac operator is given by EA dot nabla A nabla DAA. So here I'm assuming that A is an orthonormal basis, and if we take this sum, then that is how we can define this family of Dirac operators. Nabla TA is just the associated connection on SM tensor at P to nabla T and the G2 instanton A. So we have this family of Dirac operators, and using this formula, we can actually relate this. We have this relation between the Dirac operator at any time t and the Dirac operator at time 0, or the Dirac operator associated to the Levi-Civita connection. So we have this family, and why is we will use this family shortly when we will describe the deformations of the instanton. But before that, we need to know what do we mean by the deformations of an instanton. So for this lecture, we'll focus only on the infinitesimal deformations. And by infinitesimal deformations, so if you recall from before, one of the equivalent definitions of a G2 instanton was given by Fa dot eta equals to 0. And if we linearize this equation, that is, if we just do d by dt of Fa plus t of f of a plus T epsilon, then maybe this, then we get the linearized instantonic condition, which is given by dA epsilon dot eta equals to 0. So in some way, in some sense, we are just looking at a deformed connection, which is AT, which is given by A plus T epsilon, and thus epsilon, you can see, must be an at P valued 1 form, since it's a difference of two connections, and we say that it's an infinitesimal deformation if it satisfies the linearized instanton condition, which is given by dA epsilon dot eta equals to 0. So here this eta is the killing spinor, the one that defines the nearly G2 structure, and and we also need a gauge fixing condition, which is just given by the dA star epsilon must be 0. So again, the definition of the infinitesimal deformation of the G2 instanton does not depend on the torsion. It will remain the same even if you are working with some other torsion. Only the properties of the spinner eta, they would change. So in our case, eta is a killing spinner, but if in any other torsion case, eta might not be a killing spinner, it will be something else. Okay, so this is how we define the infinitesimal deformation of the G2 instanton A by these couple of equations. And as I already mentioned, the goal for these lectures for this lecture is to describe the infinitesimal deformation space. So by describe, I want to say that we want to set the space of infinitesimal deformations isomorphic to some space which one can try to compute, because just solving these two equations might not be very handy in all the conditions and all the situations. So we will try to describe it in some simpler way, which is probably easier to compute. All right, so that is what is step 1, and step 1 is just identify the space of infinitesimal deformations to the kernel of the family of Dirac operators. So if you remember, I defined this family of Dirac operators DTA, the Dirac operators associated to nabla T and the G2 instanton A on SM tensor at P, and we can prove that if epsilon is an infinitesimal deformation of the nearly G2 instanton A, then it must satisfy this eigenvalue condition for every T. And since if you remember, DTA, if we have this relation, that's why if it satisfies this condition for one of the T's, it will satisfy the condition for every T. So here we only need epsilon to satisfy this condition for any one of the T's, because they are all very related. So it's an equivalent condition. So now we can see that this epsilon, if it's so now we have identified this this infinitesimal deform to the, so I should not say kernel, the correct word is eigenspace, to be honest. So it should be an eigenspace of the Dirac operators, which in some situations is much easier to compute, as we will see in the homogeneous nearly G2 manifolds case. All right, so I'll just give a very brief proof of this proposition. So first of all, we will compute what is D0A epsilon dot eta. So this one is related to the Levi-Civita connection and the G2 instanton, and we will use the same. We will use the definition of the Dirac operator, and that gives us that we can open this up as dA epsilon plus dA star epsilon dot eta minus half EA dot epsilon dot EA dot eta. So you can just break up the nabla in within epsilon and eta, and you will get these two different components. And this thing you can compute using basic properties of the Clifford multiplication, and we get that for 7 dimensions, and since epsilon is a one form, you get that this is minus 5 over 2 epsilon dot eta, and then we can use that dTA is D0A plus D by 2 phi, and this dot is the Clifford multiplication, and we can get that dTA is given by this. So we just plugged in D0A from above, and we knew that since epsilon dot eta is in Tm dot eta subbundle of the spinner bundle, the eigenvalue for that is given by -1. So phi acts on epsilon dot eta as a minus of epsilon dot eta, and thus if we just plug in everything from here and here, we get that dTA is dA epsilon plus dA star epsilon minus d plus 5 over 2 epsilon dot eta. And now if you look at these, if epsilon is infinite, if epsilon is an infinitesimal deformation, then we know that these two terms will vanish, because dA star epsilon is 0 and dA epsilon dot eta is 0, and thus we get the eigenvalue condition. Vice versa, if we have that dTA is in this eigenspace, epsilon dot eta is in this eigenspace of dTA, then since dA epsilon dot eta and dA star epsilon dot eta live in complementary spaces or orthogonal spaces. So basically dA epsilon dot eta is in lambda 2 dot eta and are in orthogonal spaces. We can say that both of them must individually be 0, and from here we know that epsilon must be an infinitesimal deformation. So this is an if and only if condition, and that's why we are able to identify the space of infinitesimal deformations with this eigenfamily of a Dirac operator. So this is just a very brief sketch of the proof, and now we can use this identification to prove some results about the G2 instantons on nearly G2 manifolds. And for that we will use the Schrodinger-Lishnover type of formula, which was proved by Thomas Agricola and Ilka Agricola and Thomas Friedrich in 2004, and they proved it for the family of the torsion of totally skew symmetric torsion connections, and for that we can actually prove that the square of the Dirac operator, the action of the square of the Dirac operator on any spinor can be written just in terms of the base manifold M and the rough Laplacian. So here one thing to observe is that we have T over 3 on the left hand side, and on the right hand side for the rough Laplacian we have nabla T. So this type of rescaling has been seen even before, and basically if we choose this rescaling, all the terms which involves the principal bundle and the base manifold, or the mix of them, it just cancelled out, and you are only left with the terms involving the base manifold. And now from this equation you can compute for in our case for the nearly G2 structure, we knew all of them. So we know what is d phi, we know what is norm of phi square, we know the scalar multiple, which is just a scalar, the scalar curvature, which is just of course a scalar. So we have all of these things, and we can just plug in all the values, and this is what we get for with d phi equals to 4 psi. So we can see that this is a very simple expression, and we can use this expression to prove some result. So basically we can prove that if the structure group G of the principal bundle P is abelian, then our G2 instanton must be rigid. So what we do in case the manifold M is compact, so what one can do is just integrate both sides, and then we use the fact that G is abelian to show that the left hand side we know that it's an eigenspace of, since if epsilon is an infinitesimal deformation, then we know that the left hand side has to be a scalar multiple of epsilon dot eta. The right hand side we can compute, and then we can show that by a positivity argument that the instanton A must be abelian, must be rigid, or epsilon must be 0 if the Lie group G is abelian. And similarly we can also have some bounds on this operator, on the eigenvalues of this operator, and so Gonzalo and Gavin, they showed that if the eigenvalues are smaller than 6, then the instanton must be rigid, and then I showed in my work that if the eigenvalues are greater than -28/5, then the instantons must be rigid. So, and if all the eigenvalues, so if all the eigenvalues are greater than -28/5, or if all the eigenvalues are smaller than 6, then one can say that the instanton is rigid. So these are some quick checks to see if the instanton is rigid. They do not tell you anything about what happens when these conditions are not met. Then it does not say that the instanton cannot be rigid. It's just a sufficient condition, not necessary. And so from here one can also draw some conclusions that flat G2 instantons are rigid, or nearly G2 instantons are rigid, and one can also say if all the eigenvalues of this operator are equal, then also your G2 instanton must be rigid. So these are some quick theorems that one can prove about the rigidity of nearly G2 instantons, but they are useful, and we will also see how we will also use them while we will study the deformation space of the canonical connection, but that's for the next lecture, and this is it for this one. So thanks a lot for listening, and I'll see you for the next lecture, which will be the last lecture in this lecture series. Okay, thanks a lot. Bye.